Hello, this is Math Jazz from Almost Cool. This is the second live stream where we will answer your calculus questions. If you have any questions, you can email them to mathjazz9@gmail.com. So I will put that up here at the top of the screen. Email questions to mathjazz9@gmail.com. Okay, so as we have no current questions on the docket, I will write up my own. Just clear some space. So our first question is is the derivative of sine of x cubed plus 3x. So what we have here is an example of when to use the chain rule to find the derivative of a function. So first we have to identify what the outside function is and what the inside function is, or if there are multiple functions nested in each other, what each level is. We have to split this compound function here into a bunch of simple functions that we know the derivatives of. So I will split this as sine of x. Let's put that into text form. Sine of x as our outsidemost function. And on the inside we have this polynomial. So that'll be x cubed plus 3x. And I am reasonably sure that I can take the derivative of each of the functions that are listed. That is, I can take the derivative of sine, and I can take the derivative of this polynomial. So I'm going to take the derivative of sine, and I get cosine of x. And I take the derivative of x cubed plus 3x to get 3x squared plus 3. And I've taken all of my derivatives now of each of the component functions of my compound function. So now I just have to plug them in correctly into my chain rule. Find my mouse. Here we go. So our outside function is cosine of x. That's this function here. I have to plug this function into it now. So I plug in x cubed plus 3x. And now I'm done with the first line of this table. I do the same thing with the second line, but since there's nothing diagonally to the left of it, I know I am done with my problem. So I plug in 3x squared plus 3. And now this is the derivative of my compound function. The derivative of the function up here, sine of x cubed plus 3x. So that isn't so bad. Actually, we should do another chain rule problem. So while I'm thinking about it, let's do e, and let's put this in a text box. So we get e raised to the, let's have the square root of x to the third plus x squared. This is a slightly more complicated problem, but it still uses the chain rule. I have to divide this into pieces that I know the derivative of. So e to the x looks like the, there we go. E to the x looks like what I'll take as my outside function. And the inside function will be the square root function. And inside of that, we have the polynomial x cubed plus x squared. I have to take the derivative of each of these. The derivative of e to the x is e to the x. The derivative of the square root function is 1 over 2 times the square root of x. And the derivative of this polynomial is 3x squared plus 2x. So, with this, I can now do the same thing I did with the previous function. I start with the top line. The derivative of the outside function, I plug the inside function into it. And then I have to go all the way down the column, plugging each function into the one above it. So, to see what I mean by that, I have e raised to the x is this function here. But I have to plug this function into it. So this becomes e to the square root of x. But I have to plug this function into that one. So I get e to the square root of x cubed plus x squared. And now that I've hit the bottom of my column here, I am done with the first line. So now I go to the second line. I have 1 over 2 times the square root of x. So I'm going to multiply by 1 over 2 times the square root of x, which is the same as just dividing by 2 times the square root of x, like so. But then I have to go diagonally to the left, and I have this polynomial. So I plug this polynomial into this function. I get x cubed plus x squared. And since I've hit the bottom of the left column, I'm now done with the second row, and I move to the third. So I multiply by 3x squared plus 2x. And since there's nothing diagonally to the left, I am done. And this is the derivative of my function. So these aren't so bad. Taking derivatives using the chain rule is not so hard. But let us move on to another question. So, this question is going to involve implicit differentiation, which is really the same as our chain rule. It's just that now we're not necessarily solving for a function before taking the derivative. That is, normally we have y on one side of the equation and a bunch of stuff involving x on the other, and we take the derivative to get y prime. When we do implicit differentiation, we don't always have a function that is solved in terms of x. That is, it's not going to be y on one side and a bunch of stuff with x on the other. Sometimes the x's and y's mix in a way that we can't split them apart. So what we do is, well, there is a very technical reason for why we're able to do this, but we're basically able to ignore the fact that we're not solved for a function so long as we remember the chain rule. Whenever we see a y and we take a derivative of that y, we're going to multiply by y prime, because y is going to be our inside function. Whatever expression has y, like 3y squared, our outside function is 3x squared. But our inside function is y. We have y plugged into this other function. And so when we take the derivative, we're always going to have to multiply by our inside function, just like we do for the chain rule. So, with that said, let us find the derivative of this implicit statement, this implicit function. We have, let's put it into a text box. We have y squared plus xy equals 10. Here is an implicit function. That is, we can somehow think of y as depending on x. We graph our curve that this equation corresponds to, and then we just take chunks of the curve that satisfy the vertical line test, and those are implicit functions that come from this equation. We can take the derivative of this. So we get 2y times y prime, because our outside function is x squared. So we have our outside function, our outside function, x squared. Its derivative is 2x, and we plug in our inside function, which is y. And then we multiply by the derivative of y. Actually, let's do this one time before I move on any further. We'll do it one time using our chart. So our outside function is is x squared. And our inside function is y. So the derivative of x is going to be 2x, and the derivative of y is y prime. So using this chart, our outside function, here's our cursor, our outside function's derivative is 2x, and we plug in y. So we get 2, we get 2y by taking this function here and plugging that function into it. And then we have to multiply by, the derivative of y is, in fact, y prime, not 2y prime. The derivative of y is y prime, and there's nothing down here to plug into it, so we get y prime. And now this is how we see that the derivative of y squared is 2y, y prime. And now the next part. We have a product here. So we take the first function and multiply it by the derivative of the second function, derivative of y is y prime. And then we're going to take the second function and multiply it by the derivative of the first function. But the derivative of x with respect to x is is 1. Derivative of x with respect to x is 1. So y times 1 is just y. On the other side, we have a constant, so its derivative is 0. So, just checking to see if we have anything on chat. It looks like we don't. And we'll go back to the problem. So now we need to solve for y prime. So I'm going to factor a y prime out of the first two terms. So y prime times 2y plus x. And we're going to subtract the y to the other side of the equation, like so. So what we have is y primes being factored out of these two terms, and a y being moved to the opposite side of the equal sign. And now we're going to divide both sides by 2y plus x. So we get y prime equals negative y divided by 2y plus x. Like so. Now, I'm wondering if I'm able to graph this. This object here, y prime equals negative y over 2y plus x. is something called a vector field. And I'm wondering if I can figure out the commands on air on how to graph one of these things. So let's see if I can figure this out. So let's see. Plot 3D. It's not exactly what I'm looking for. I will have to look that up before next week. I'm sure that Mathematica can do it. But for now, we can do a plot 3D. So let's do this. This is going to be a 3D graph of our derivative of this implicit curve. And let's graph it from x equals -10 to 10, and y equals -10 to 10. I think this will do it. Oh, here we go. Let's see, can I make it bigger? Yes, I can. So the height of this graph represents the slope of the curve. Like, so for example, if I plug in whatever this x value is here on this line, whatever this y value is here on this line, if I plug in this point on the graph, I'm going to get out whatever this height is on the graph, and that represents the slope of the tangent line to this curve at that point. You're wondering, but this is a curve, and this here is a sheet. It's two-dimensional, and this is, sorry, it's a 3D graph, but the object graph is two-dimensional. See, like, you can think of taking a sheet and maybe bending it into this shape, maybe having to tear the sheet a little bit to get it to fit exactly right. Anyway, that's true. You're losing the information of this this constant here, this 10 here, and so if we were to graph this, maybe we have an implicit plot function. Plot. Let's see. Plot region. Yeah, I will have to think about how to do an implicit graph in Mathematica. I know that there's a way to do it. I can't think of it right now. But what happens is that you'll have to, when you look straight down on this graph, you have a y-axis running north and south, and an x-axis running east and west, and you plot your curve, and then you can take the heights on this 3D graph here that correspond to points that lie on the curve. What happens is that if you change this constant, it changes what curve lies in the plane, and so it changes which heights you're able to pick for your dy dx. That might have been complicated. I might need to make a video about implicit curves and derivatives. Oh, so we want to do a review of a problem. Let's see. Review number 16. So, let's see. So we want to calculate y prime. Okay, let's clear all of these off the screen. So this problem is what I think we're being asked for on the chat. So we have u minus 1 divided by u squared plus u plus 1. And the whole thing raised to the fourth. Is this the question that we were asked for, chat? I'm going to find y prime for this. And chat can tell me one way or the other. So let's see. So I want to find y prime, and I can use the quotient rule, but I'm going to actually use logarithmic differentiation here. So I know that y is equal to that. And so that means that the natural log of y is equal to the natural log of this expression. But the natural log says, the natural log allows us to split apart powers and products. So I'm going to rewrite this as 4 times the natural log of u minus 1 minus 4 times the natural log of u squared plus u plus 1. I can do this because the numerator becomes, well, the numerator is raised to the 4th power. 4 becomes my coefficient, and what was raised to the 4th power is the argument of natural log. And then the bottom becomes negative because division turns into subtraction inside of a log. And then the power 4 comes down in front, and we get this denominator here. This denominator that was raised to the 4th power becomes the argument of the natural log. So I get ln of y equals this. And now I can take the derivative much easier. The derivative on the left side is going to be y prime over y, using our implicit differentiation, and the fact that the derivative of the natural log of something is the derivative of that something divided by the original function, and that will be equal to 4 times the derivative of u minus 1, which is 1, divided by u minus 1, minus 4 times the derivative of u squared plus u plus 1, which is 2u plus 1, divided by our original function u squared plus u plus 1. So this here is our derivative divided by y, not our derivative. So we have to multiply by y to get our actual derivative at the end. The derivative we were looking for, the derivative to that. And we remember that y is equal to our original function. So we're going to multiply by this on the right and y on the left, since those two things are equal to each other, and we get y is equal to this function times the right-hand side of the equation above. And this is our derivative. Okay, So I'm going to look up another problem to do from chat. Let's see. Bear with me. So we were asked to do number 3. Okay, so this problem, and I'll clear this in a little bit. We're asked for if f of x equals a times sine of x, sine of cx, plus b times cosine of cx, where a, b, and c are constants, then what is the second derivative of f? Apparently it doesn't quite like parentheses. There we go. So we want to take the second derivative of f, and we will clear the screen because you can pause the video if you want to look at things for a little longer than they're on the screen. Plus, you can also rewind the video if something is gone and you want to go back to it. So we want to find the second derivative of this. So the first derivative is going to be, well, we have to use the chain rule. So we're going to get a times the derivative of cosine, the derivative of sine, which is cosine, of cx, times the derivative of cx, which is c. Plus b times the derivative of cosine, which is negative sine, with the cx plugged into it. And let us go flip the sign to be negative. And then we multiply by the derivative of cx, which is c. And so this is our first derivative. So let's write that like that. F prime of x is equal to AC times cosine of cx minus BC times sine of cx. And maybe we'll put this in traditional form. Oh, it's a text box, so it doesn't execute code. There we go. It also needs these to be square brackets to treat it like a function. There we go. So now we take the derivative of this to get the second derivative. So we have our traditional form box. We go f double prime of x equals, and we take the derivative of AC cosine of cx, which gives us negative AC cosine of x, of cx, and we multiply by the derivative of c, which means that we get c squared. And we'll do the same thing on sine. We get BC, and I'm going to put the squared there anyway because I know it's coming, sine of cx. Right. Sorry, the derivative of cosine is sine. See, I almost forgot. Cosine turns into sine, and sine will turn into cosine here. There we go. So this is our final derivative. This is the second derivative that we were asked for, and in traditional form it looks like this, although that looks a little bit ugly. Maybe if I do that, it'll come out nicer. That's better. Okay, so that is the second derivative of the function given. Okay, so now let's take the derivative of x plus 1 over x minus 1. We can use either the quotient rule or logarithmic differentiation for this. Since I'm kind of in a logarithmic differentiation kick, I'll do it that way. So y equals this. So when we take the natural log of both sides, we get natural log of y equals, and I'll simplify this, we get the natural log of the numerator minus the natural log of the denominator. And we'll take the derivative, and we get y prime, because that's the derivative of the thing inside of the log, divided by y, because that's the thing that's actually in the log. That'll equal, again, the derivative of this function is 1, and then we divide that by this function, so you get 1 over, there you go, 1 over x plus 1 minus the derivative of this is 1, and then we divide it by that function, so we get 1 over x minus 1. And then we solve for y prime. Y prime is equal to, we multiply by y on this side, and since y is equal to this fraction here, we'll multiply the right side of the equation by this. If we wanted to, we could write it in two steps, where we first multiply by y on both sides and then we substitute. But we'll do it this way. It's one less line of writing. So we get our original function times the right-hand side of this equation. So there. Okay, so let's pick another problem from my list of problems. So I think I've caught up to the requested problems on the docket. So let's see. Let's go to, this one looks nice. So I'm going to kill these. And I want to show that the equation 2 raised to the x plus 4x equals 0 has exactly one solution in the interval -1 to 1. So the first thing to do is show that this has a solution at all. And so I'm going to plug in 1 and -1 and see what we get. Oh, I guess for the first thing we have to do is we note that if f of x equals, and we'll let f of x equal 2 to the x plus 4x, then f is continuous on the interval -1 to 1. So this means that the intermediate value theorem will apply to this function on this interval. So we note that f of 1 equals 2 plus 4, which is 6, which is bigger than 0. And f of negative 1 is equal to 1/2 plus, well, minus 4, which is equal to negative 3.5, which is less than 0. So by the intermediate value theorem, we know that there is a root between negative 1 and 1. So now that we know that there is a root, we have to prove that there can't be more than one root. And so we're going to assume that there are two and come up with a contradiction. So here we go. So we have suppose that there are two roots of f. Call them a and b. F is a differentiable function so so the mean value theorem applies. Now we note that the mean value theorem implies that there is a C between A and B such that f prime of C is equal to f of B minus f of A divided by B minus A. And I'll get all of my parentheses in place in a moment. But we also know that f of B is 0 because B is a root, and f of A is 0 because A is a root. So 0 minus 0 is 0. So we get that this is equal to 0 divided by B minus A, which is 0. So somewhere our derivative equals 0 because we have two roots. Now we'll take the derivative of our function. We get 2 raised to the x times the natural log of 2 plus 4. And we're told that when we plug, so this is f prime of x is equal to this. And we suppose that this is supposed to equal 0 somewhere between negative 1 and 1. So f prime of C is that point where it's supposed to equal 0, is equal to 2 raised to the C times the natural log of 2 plus 4. But here's the problem, is that, this is equal to 0. Then that means that 2 raised to the C times the natural log of 2 is equal to negative 4. And that means that 2 to the C is equal to negative 4 divided by the natural log of 2 which, let's calculate this for a second. We get negative 4. Oops. Negative 4 divided by the natural log of 2. Mathematica defaults so that log means the natural log, not the common log. So that is just how Mathematica does it. We will calculate this, and I forget again, we need to force it to convert to a decimal. So we get negative 5.77 as the value here. Now we know that the smallest value of 2 to the c, well, 2 to the c is a positive number. That's the problem, is that since 2 to the c is a positive number, that means that somehow this positive number equals this negative number, and that's a contradiction. That might have sounded a little disjointed to everyone. 2 to the c has a horizontal asymptote at 0. It's always positive. There's no real power of 2 that is negative. But somehow 2 to the c is negative. That's not possible. So we have a contradiction. So, since 2 to the c is not a negative number, we have a contradiction. It means that our assumption must have been wrong. But the thing we assumed was that there are 2 roots of f. So that means that there cannot be 2 roots of f. Now, since there can't be 2 roots of f, and there is at least 1 root of f, we know that there's exactly 1 root. And now we're done. Because the root of f is equivalent to this equation being true. That is 2 to the x plus 4 times x equals 0. Okay, let's work on another problem. Okay, so this problem that we'll work on, we're going to find the derivative of this function. We'll have f of x equals 3 plus x cubed raised to the sine of x power. This is a fairly difficult question. We need to use logarithmic differentiation because we have a variable in our base and in our exponent. If one of those two things were constant, we could either use the power rule or we could use the chain rule and the derivative of e to the x. But since both of these are variables, neither the exponential rule nor the power rule will work. So the first thing we do is we'll take the log of both sides. We get the natural log of f of x is equal to sine of x times the natural log of, I'm going to switch the order here, x cubed plus 3. You don't have to switch the order. I like having the leading term of my polynomial being the highest powered term in the polynomial. And now we're going to take the derivative of both sides. So we get f prime of x, because that's the derivative of what's inside the log. And then we divide it by what's actually inside the log, which is f of x. That equals, here we have a product, so we get the derivative of the first function times the second function. Plus the first function times the derivative of the second function. The numerator of our fraction will be the derivative of what's inside the log, 3x squared. And then the denominator of our fraction will be what's actually inside the log, which is going to be x cubed plus 3, like so. And now, to solve for f prime, we have to multiply both sides by f of x. We get f prime of x is equal to this thing on the right-hand side, divided by our original function. Not divided by, multiplied by our original function. There we go. If I change all of these to brackets, then I can do a traditional form, and it might look clearer what's going on. Let's see. There we go. So we can see our original function is here, and this is all of the stuff that happened after we took the derivative, but before we multiplied both sides by f of x. Okay, so the derivative of, this is a question on chat, a raised to the x is a raised to the x times the natural log of a. And it happens that when you let a equal e, the number that's slightly less than 3 and is the base of the natural log, you get the derivative of e to the x is equal to e raised to the x ln of e, but ln of e is 1, so you're left with just e to the x. Does that help? Wait for chat to catch up to us. In the meantime, let's do another problem. Let's see. So, in this one, we have water flowing into an inverted cone at a rate of 4 cubic feet per minute. Inverted will mean that the point is down. That'll actually make the math quite a bit easier. The point we're on the top, it would be a slightly more complicated problem, but this way is easier. Suppose that the radius is half the height. How fast is the water, is the depth of the water increasing when the depth is, let's say, 4 feet? Okay, so let's do this problem. So the first thing to remember is that the volume of a cone is equal to 1/3 times pi times the radius squared times the height. Now, one thing we're told is that the radius equals half the height. And we also know that we're looking for the height, or at least the speed at which the height is changing. So we're going to kill off r using the substitution that we're given of r equaling half of the height. So this is going to give us the volume is equal to 1/3 pi h over 2 squared h, or that'll be v is equal to 1 over 12 pi h cubed. Okay. Actually, I'm going to move this 12 to the end. So pi h cubed over 12. There we go. And now we're going to take the derivative. So we get dv over dt is equal to pi h squared over, now the 3 came down, and the 3 cancels with a 12 and leaves us with a 4 in the denominator. So we get dv dt equals pi h squared over 4 dh dt. There we go. So we know that at the time that we're interested in, dv dt is 4 cubic feet per minute. The volume is increasing by 4. And we know the height, or the depth, is 4. So that's going to be pi times 4 squared is 16, divided by 4 times dh dt. We can, of course, cancel a 4 from the top and the bottom of this fraction. So we get 4 pi dh dt, and we'll cancel a 4 from both sides, and we'll divide by pi on both sides. And we get that dh dt is equal to 1 over pi. So that's not so bad. 1 over pi means that it's slightly less than 4 inches per minute. Okay, so let's do one more problem before the end of the show. Let's pull this up. Let's see. This is one that I think is interesting. I'll delete the cells on the screen. And this will be the last one that we do tonight, I think. So we're going to find the derivative of arctangent of x using implicit differentiation. Okay, so first we know that y is equal to arctangent of x, and that is exactly the same. I think this is the right symbol for this. Yes, it's the right symbol. That's exactly the same as x is equal to tangent of y. So we use x equals tangent of y, and we take the derivative implicitly. So we get 1 is equal to, the derivative of tangent is secant squared of y, and we multiply by y prime. Because the outside function was tangent x, the inside function is y. So the derivative of tangent is secant squared, plug in the y, because that's our inside function, and then multiply by the derivative of the inside function, which is y prime. And then we solve for y prime, so we get y prime is equal to 1 over secant squared of y, but 1 over secant squared of y is equal to cosine squared of y. So we might as well not have the fraction if we can avoid it. Now, here we have to figure out what cosine squared y is in terms of x. And maybe I can get a nice triangle for a diagram. Nope. Maybe this is how to do it. Triangle is not a graphics primitive? That's sad. Okay, well, here's a triangle. Let's have a graph of 0 and the graph of negative x over 2, and you'll just have to imagine the third side of the triangle. There we go. Here's our triangle. And you'll just have to imagine a vertical line here, because I'm not going to put one in just yet. Well, I'm not going to waste the time to figure out how to put it in right now. So, if we know that x is equal to tangent of y, that means y is the angle down here, and x is equal to this side, the opposite, divided by this side, the adjacent. So the cosine is going to be the adjacent divided by the hypotenuse. Let's label these sides of the triangle. So the opposite side we'll call x long. The adjacent we'll say is 1 long. The reason we pick x and 1 is because we need the tangent to equal x. And the tangent is the opposite divided by the adjacent. So if the opposite is x and the adjacent is 1, x over 1 is definitely x. And now we're going to have to use the Pythagorean theorem to find out the hypotenuse. But we know that the hypotenuse squared is equal to the square of the opposite plus the square of the adjacent. So that'll be x squared plus 1 squared, which is 1. So we can take the square root of both sides, and we get the length of the hypotenuse. Like so. So now we know the length of each of the sides of this triangle. And we know that y prime is equal to cosine squared, which is going to be the adjacent side, which is 1, divided by the hypotenuse, which is the square root of x squared plus 1. So this is equal to, remember the whole thing is squared, 1 over square root of x squared plus 1. And then we know that we can split up this fraction like so. We get the square of a fraction is the square of the top divided by the square of the bottom. So we just take, instead of taking the fraction and squaring it, we square 1 and get 1. And we square the bottom, where the square root and the square will cancel, and we're left with x squared plus 1. And this is now the derivative of arctangent of x in terms of x, and the solution to our problem. So with that, we will call it a night, and we will wrap up this episode. If you want to rewatch this, this will be posted to the YouTube channel. And so thanks for watching. I hope you have a great day.